I've added a little stereo system. If we put that in reverse, I've got a screen that pops out and shows me a rear view of the car. With the top up on this Porsche, the rear visibility is quite limited, so we added a rear view camera in a license plate frame around the back of the car. We've kept all 4 gears and the clutch as part of our drivetrain, but I rarely use but 2 of the gears, and I almost never use the clutch. The inertia of the net gain warp 9 motor, or the mass of the rotor, simply isn't a match for what we had with an internal combustion engine. And this does a couple of things. One, I can shift going down the road with no difficulty and no use of the clutch. When we pull up to a stoplight, if I take my foot off the brake, again, the car is not, it simply removes power from the net gain warp 9 motor, and we're sitting at the stoplight not using any energy, maybe a little bit for the cooling air blower in the car. And the other thing that happens is that going down the road, the power band on an electric motor is so much wider than on a internal combustion engine. Third gear lets me take off with great acceleration, and is good up to about 55 miles per hour, 80 kilometers. And then if I'm on a freeway and exceed that, I drop it into 4th gear, and I can go again. So top speed of about 85 miles an hour. Largely a function of our battery configuration, not really the motor or the controller. And that's pretty much the case. The other thing that happens with that lack of mass and inertia from a combustion engine is that if you pull up and put it in gear and turn it off and get out and walk away from the car, it's quite likely it'll roll down the hill and right into the river. So a good handbrake is an absolute necessity on an electric car because there's nothing else holding it. There's no park with a manual transmission, and there's no engine to keep it from rolling away if it's in gear. So the only thing holding the car in position is your handbrake. Okay. So to take off, we're going to put the car in gear, release the handbrake, and apply a little bit of brake pedal or accelerator pedal, and we'll be rolling. Do be on the lookout for pedestrians, as they cannot hear us approach, and so they don't automatically get out of the way. The same can be said for wildlife. The good news is your stereo will sound a little better, but the quietness of the electric car is one of its greatest benefits. The other is the smooth application of power. On acceleration, the electric drive simply does not have the staccato bands of power that an internal combustion engine does. From 0, this car accelerates smoothly and continuously up to about 55 miles an hour. At that point, the back EMF of the motor is pretty much equal to our battery voltage, and we have to shift from 3rd to 4th gear to get another acceleration band from about 55 to 85. The experience is nothing like a golf cart. It's quite unlike anything you've had in a car. It's just a continuous acceleration. It can be quite exhilarating. As we mentioned, the other notable difference with an electric car is when you take your foot off the accelerator, the car doesn't slow down. In fact, if you're going downhill, it may well speed up. And this is, again, one of the benefits once you become accustomed to it, is that you can travel sometimes quite a distance without applying any power at all. There's a number of benefits to operating an electric car and owning one, but I'd roughly put them into 3 categories. The first is technical elegance and efficiency. The second would be costs. The third, of course, is the environmental impact and lack of emissions. The cost benefits, the environmental benefits, and really most of the benefits of an electric car really derive directly from the first part of the discussion, and that is that the electric drive system is simply more efficient at converting stored energy into forward motion. To talk about this, we have to establish some terms. We measure energy storage in an electric car in kilowatt hours. A watt is the amount of power used to establish a 1 volt difference in potential at 1 ampere of current flow. And consequently, a kilowatt would be 1,000 watts. Now, that could be any combination of voltage and current. In this particular car, we have a pack voltage of 100 volts. So at a 10 amp drain, we're burning a kilowatt. If we did that for an hour, that's a kilowatt hour. This battery system is capable of storing about 21 kilowatt hours of energy. Because we want to limit the battery usage to 80% of what's stored to prolong the life of our batteries, that leads us to about 16.8 kilowatt hours of stored energy. In actual operation, at an average speed of 40 or 45 miles an hour, we're probably averaging 100 amps of current. As a result, this vehicle burns about 10 kilowatt hours per hour of operation. Another way to look at this is the number of kilowatt hours or watt hours of energy burned per mile. To travel a mile down the road, this vehicle burns between 225 and 250 watt hours of energy. And that's a function of how we drive it. If we're on the freeway, it could be as high as 300 watt hours per mile. But trolling around town, it's about 225 watt hours per mile, which gives us a range of about 75 miles. Roughly, we're getting a little over 4 miles per kilowatt hour of stored energy using this electric drive system. Oddly, this is about the same efficiency we had 100 years ago. The technological advance is, of course, we can go 85 miles an hour, and they typically went 11 or 12 miles an hour. But the range that we derive from energy stored in batteries is almost identical to where we started over 100 years ago. Similarly, in terms of efficiency, while the gasoline engine has suffered some remarkable improvements over the last 100 years, and instead of going 8 to 10 miles an hour, we can now easily drive a car 200 miles an hour, the efficiency really hasn't improved that much. 100 years ago, you got about 20 miles per gallon. As of the end of 2008, our national fleet average across 244 million vehicles is about 21.3 miles per gallon. While we don't normally talk about the energy content of a gallon of gasoline, we're rather forced to compare the two systems. A gallon of gasoline stores the equivalent of about 125,000 BTUs of energy, or 37 kilowatt hours of electrical energy. So to go 21.3 miles on a gallon of gasoline, we're using the equivalent of 1,737 watt hours of electrical energy, compared to the electric vehicle's 225 or 250 watt hours. You'll often hear that the internal combustion engine is about 25% efficient. Well, it's not. It may be 25% efficient in a laboratory with nothing hooked up to it, but when putting gasoline in one end and taking miles out the other, this would imply an efficiency of between 10 and 11%. And by comparison, the electric drive system, while it's also typically the motor is 88 to 92% efficient, it loses some efficiency through the drivetrain down to about 80%. The heart of all the advantages coming from an electric drive automobile derive from this fact that they're 8 times more efficient than the internal combustion engine.